Welcome to the Chapter 18 Energy and Mineral Resources lecture. This lecture is going to be broken into two pieces because this is a big and important chapter. What I hope to get through in this lecture and what I hope you grasp from the chapter in your reading is a better understanding of the formation of and exploration for energy resources, the trade-offs that are involved in different energy sources, the formation of and exploration for mineral resources, and the importance of mineral resources in society. So the first question in your notes gets at that importance. What do you know about energy and mineral resources already? Well, hopefully you know that after water and soil, energy resources and minerals are the next most important natural resources. Energy is important for transportation, for factories, electricity, so you use it every day in every moment, every aspect of your life. You are drawing on mineral resources. So the rule of thumb is if it didn't grow out of the ground, or if it didn't grow as a living being, then it came from geology. It came from mining it out of the ground. All of the plastic and metal and various minerals in your computer right now all had to be mined out of the ground. All the pieces of your car, even the plastic in your pencil, the materials that are making the building that you're sitting in right now. All of these originally came from the ground, being mined out of the earth. So mineral resources are important for material and products. So when we're talking about energy and mineral resources, one of the first places we think of is the Arabian Peninsula. And why is that? So we want to observe this area, take a look at this region around the Arabian Peninsula, because it is the world's largest source of petroleum. So this area produces 1/4 of the world's oil. They have 57% of the oil reserves in all of the world, and 45% of the gas reserves. The peninsula is mostly the country of Saudi Arabia, with Iraq and Iran to the north and east of the Persian Gulf. The Persian Gulf region produces, like I said, 1/4 of the world's oil. That's about 23 million barrels per day. And again, nearly 60% of the world's oil reserves, so 57% of the world's oil reserves. So why? Why do they have this abundance of this natural resource? To understand that, we need to look at the geologic setting. When we look at this map, it shows the tectonic features near the Arabian Peninsula. The oil and gas fields are shown in green and orange, and areas where Precambrian rocks are exposed are in gray. Okay, so we can see that this whole area where it shows us the Arabian Shield is in gray, so that's all Precambrian rocks. And we can see the direction that these faults are moving using our key. So if it's a transform fault, it has side-by-side arrows. If it's a thrust fault, it is being thrust or overriding the other plate in the direction that those teeth are pointing. Okay, and where you have the side-by-side lines, the parallel lines, that's showing us a divergent boundary. So the Red Sea Rift is just that. It's a rift. Saudi Arabia is getting further away from Africa along that rift. So taking a look at that in cross-section, we can get a better idea of what's going on. The Persian Gulf is a convergent boundary where the Arabian Plate is under the Eurasian Plate, and where that occurs is the Zagros Mountains. Okay, so you can see that in the map version, the Zagros Fold Belt is what it's called. The Red Sea is a divergent boundary between Arabia and Africa, and flanks of rift uplifted, exposing Precambrian basement. So as that divergent boundary is pushing apart, as it's diverging, it's uplifting on the sides. It's compressing from that pressure that's being exerted, and it's lifting up into the air, bringing up older Precambrian basement rocks to the surface. And Arabia is tilted and uplifted on the west and loaded on the east. That means if you look at the cross-section, you can see the layers are sloping down. They're higher in the west and loaded in the east, meaning there are more layers pressing down in the east. And so all of this is important because oil migrated up from buried and heated sedimentary rocks in this area. So that's where we get these oil fields, and you'll notice they're on top of salt domes, and we'll get at that. We'll talk quite a bit about salt domes in just a moment. And here's another view of the Zagros Mountains, so you can see the result of that compressive stress there, of squeezing those plates together. This is what happens. So that is the geologic setting of this region. Now we know that Arabia has a lot of oil, but why is that? To understand that, we need to look at the geologic history of the area, and now we know that because they have oil, they had to have these specific types of environments. So before I go into where petroleum comes from, I want to explain a bit what is petroleum. Petroleum is an organic, meaning it was previously alive. It does not have anything to do with organic like we do in the grocery store as far as grown with pesticides and all that good stuff. It is a previously living substance, okay, an organic substance composed of carbon bonded with hydrogen and small amounts of other elements. So we call those hydrocarbons. Okay, so petroleum is a previously living substance, an organic substance composed of carbon bonded with hydrogen and small amounts of other elements, also known as hydrocarbons. Alright, so now where does petroleum come from? Oil and natural gas occur together when sediment-rich organic material is deposited, buried, and heated slightly over time. Some rich sources of organic material are coral reefs, small microscopic ocean life, and algae such as kelp. Swamps on the land produce coal but not oil. Okay, so when you think of petroleum, think of an ocean environment. When you think of coal, think of a swamp environment, so on land. So again, oil and natural gas occur together when sediment-rich organic material is deposited, buried, and heated slightly over time. Some rich sources of organic material are coral reefs, small microscopic ocean life, things like plankton settling out, and algae such as kelp. Okay, the temperatures that are ideal to make oil we've got a range of 60 to 120 degrees Celsius to make oil. In making gas, usually higher temperatures are involved, okay, but never above 200 degrees C. Okay, so breaking down these images on the bottom of the screen, we have accumulation of organic material, meaning organic material dies and collects to form a rich layer of organic material, and this is going to be called the source rock. S-O-U-R-C-E, the source rock. Okay, meaning this is the source of the oil. The next one, buried and preserved in oxygen-poor conditions, the organic material is preserved by being deposited in an oxygen-poor environment. Okay, another word for oxygen-poor is anoxic, A-N-O-X-I-C. An anoxic environment has low oxygen. Oxygen is what eats up things as they're decaying. So you need to have an anoxic environment so that all of the organic material can decay just right. It's buried to a shallow depth and heated to less than 60 degrees C to form kerogen. Alright, now our last image here, buried and heated to the right temp. Over time, the source rock is buried further and heated to temps between 60 and 120 degrees Celsius. The kerogen breaks down into heavy and light oils. At temps greater than 120 degrees, natural gas forms. Okay, but again, you have to be careful not to get the temperatures too high. So metamorphic temperatures, for example, or igneous temperatures, are too high, and that will burn up all of the oil. Where do oil and gas go? So now we know where they originate, but how do we get them to the surface? So if we take a look at this image, we can see our layers are folded. So the oil gets generated at depth because we need that high temperature from deeper in the earth to have just the right conditions to generate the petroleum. Okay, so it's generated at depth. Oil and gas are lighter than water, so they float on groundwater and migrate up toward the surface. So they're flowing through permeable rocks and working their way up toward the surface, up toward an area of less pressure. So always going from high pressure to low pressure. That's what fluids and gases like to do. Permeable rocks include well-sorted sandstone and fractured layers. Less permeable rocks, like shale, can block the flow or trap oil. So this is actually necessary in most cases for getting oil out of the ground. You need to have your source rock, which is also called your reserve rock or your reservoir rock, and you need to have a cap rock, okay, something impermeable that holds it in place so all of the oil can gather over a long time, migrating up, in this case, into the axis of this fold. Okay, so again, you need to have a permeable reservoir rock, a permeable rock for the oil to migrate through, and you need to have a cap rock to hold it in place so it can accumulate. To trap oil, there must be no pathway to the surface, or else that generates what's called an oil seep. And once you have an oil seep, you can use that oil, but if it's there long enough, it's going to be degraded by bacteria. And so if anybody was a fan of the Beverly Hillbillies, that's what Mr. Clampett found when he was out shooting in the woods. He came across an oil seep. Alright, if it flows into unconsolidated sand, then you get oil or tar sands. Okay, so that's in the case of an oil seep, or even if it's near the surface and it's in unconsolidated sands, that's when you get oil or tar sands. And oil and gas are always going to flow all the way to the surface unless there's something that's blocking them, unless something stops them. So that's why you need to have the cap rock, the impermeable rock over the top, to keep it from reaching the surface.